right there, and we should be good. Here we go. Okay, good morning and good evening, and I guess good night for some of you, to everybody. We're very excited about having this webinar today with Steve Jones. I'm obviously not Steve Jones, but I'm Matthias Carlson, and I'm here with a few colleagues in the panel, including Curtis Whitson, and I'll be trying to moderate this session today. Before Steve is going to give a presentation about GOR and how we can use that as a diagnostic tool for evaluating infill well spacing, we're just going to go through a few announcements. The first thing is related to, I guess, some meeting logistics. First of all, we have a lot of participants registered for today, more than 500 actually registered participants, and on that note, we are using something called WebEx events, such that everybody except for the panelists are muted by default, but that doesn't mean that you can't interact and ask questions. There is a Q&A box or a chat box available to the right there of the screen, so if you have any relevant questions, make sure to type them in there, and I'll try my best to ask Steve if we find some natural places during the presentation, or we'll try to fit as many of these questions also in the or after the presentation by Steve in a dedicated Q&A session. The presentation by Steve will take around 45 to 60 minutes, and as I mentioned already, everything will be recorded and will be made available both on LinkedIn and on Whitson Academy. And a lot of you have asked about Whitson Academy, and therefore I'll go through a few details related to that. So Whitson Academy is essentially a product that we offer for online training related to a lot of the things we do here at Whitson. So in short, a corporate subscription of Whitson Academy includes 4 live virtual courses each year, some live topical webinars such as these, some on-demand pre-made courses that are essentially recorded and that can be accessed at academy.whitson.com, including to kind of tutorials and how-to videos of using different softwares or do certain procedures. And when it comes to some examples of the courses we have there, all of them are typically related to what we specialize in here at Whitson, and we try to cater for all different levels from beginner to expert. On that note, a lot of you have asked about the courses we are going to offer as of this year. That information can be found on our webpage on whitson.com/training, and the 4 courses that we're holding or this year is listed there, but in very short, we have the 5-day advanced PVT and EOS fluid characterization course in June. We have a 1-day course on gas condensate reservoirs, what's important and why, and then 2 shale-related courses later in the year, one related to gas GOR in tight unconventionals, and a second one related to shale PVT and sample. Throughout the year, we'll also hold more webinars like this. The next webinar is already in April. That's coming in a few months. That's a webinar with Braden Bowie from Apache, and the topic there is actually a little bit relevant to some of the parts that Steve is going to talk about today. And it's essentially presenting a numerical RTA workflow that he presented at URTEC last year. And again, you can find the registration link on whitson.com/training, and we'll also market this on LinkedIn and through other channels as that date is approaching. So on that note, I'll not take more of everybody's time. I would like to introduce the speaker, who is Steve Jones, as I hope we see on the video with Steve here. He is a reservoir engineering advisor at Cimarex, where he's been the 5 last years. So before that, he was around 15 years with the Newfield exploration. And in addition to that, he has also been filling multiple other roles after he graduated first from a bachelor's degree in petroleum engineering from the University of Tulsa, where Steve is now based out of, and where he's working for Cimarex. And he also have he has a master's degree from UT Austin as well. So on that note, Steve, I'll just stop sharing my screen here and make you a presenter, and we should be good to go.
Okay, thank you, Matthias. Hopefully everyone can see my screen.
Yep.
Okay, so we'll jump right in. I'm going to be talking about gas-oil ratio as a diagnostic tool for evaluating infill well spacing. These are the topics we're going to cover. We'll talk a little about fundamentals of GOR in linear flow, because it's very different than GOR in radial flow to vertical wells. We'll talk about how the gas-oil ratio increase during boundary-dominated flow is related to drainage volume, and that's why it's important in helping to evaluate spacing. We'll talk about how pressure normalized rate is related to drainage volume, because it also helps us to evaluate spacing and how much volume a well is seeing in terms of oil in place or gas in place. And we'll talk about the differences that we observe between parent wells and bounded infill wells. And since we're going to be talking about spacing, I want to bring up the most important topic, or the most important concept that you can have if you're going to deal with spacing, and many of you are well aware of this, and that is humility. Anyone who claims to know all the answers doesn't really know very much. Those of you who have planned spacing projects know that things usually don't turn out like you think they will, and even with all our analysis, it often comes down to some trial and error, which can be pretty expensive sometimes. So I just want to say that I'm still learning, as all of you are, and hope that I can help you along that learning path today, and that we can remain humble as we do that, because you certainly need to be. The fundamentals of GOR is what we'll cover first, and these concepts are covered in a paper from 2017, I believe, SBE 184-397. So I'd encourage you to look that up for the background of this material. But these are just some basic concepts of how GOR behaves in linear flow as opposed to radial flow in vertical wells. So if you have the luxury of having a reservoir pressure that's above the bubble point, there may be a period early in the well's life when your bottom hole flowing pressure is also above the bubble point. And at that time, the GOR will be constant at the dissolved gas-oil ratio R sub SI, as long as the bottom hole flowing pressure is above the bubble point. That's the first stage. The second stage will be when the bottom hole flowing pressure falls below the bubble point, at which time you'll see a rise in the gas-oil ratio. And on this plot on the right here, the gas-oil ratio is the red line with the scale on the left. The black line is the bottom hole flowing pressure with the scale on the right. You can see the bubble point in this case is about 2,600 psi. So when the bottom hole flowing pressure falls below 2,600 psi, very soon the GOR will begin to rise. So in transient flow, transient linear flow for given PVT and completion, GOR is going to be controlled by your bottom hole flowing pressure. Then you get to a transient plateau if the transient flow regime is long enough to observe this. A lot of times these days it's not long enough and you really don't see this. But early on, when we started drilling reservoirs and our frac stages or our cluster spacing was very wide, we typically saw this transient plateau. It occurs if your bottom hole flowing pressure is constant and you're in transient linear flow. So if you read this paper, that's all explained in there, and it's been discussed by numerous authors. Then when you go into boundary dominated flow, you will see a rise in the gas oil ratio. That's a result of the declining average reservoir pressure. And again, this idealized situation is assuming a constant bottom hole flowing pressure. Well, since I wrote that paper, fracs have changed, completions have changed. We're doing bigger fracs and closer clusters, so the wells have more productivity, and more gradual decline in bottom hole flowing pressure. So they don't follow that idealized behavior that I was showing. Typically, we're seeing short time to end of linear flow, which is on the order of 2 or 3 months, something like that, sometimes less. So we don't usually see that transient GOR plateau because the bottom hole flowing pressure is not constant during that linear flow transient period. And as you know, we're doing a lot of infill drilling now as our fields become more mature. And we're seeing the effects of limited drainage volume. So boundary dominated flow is starting earlier, within a few weeks or months. Depletion behavior progresses fairly quickly, especially if you've drilled on tight spacing, which gives you a steeper decline because you're starting at higher rates. We have more infills to deal with and fewer parents, and that has raised some concerns about the higher gas oil ratios that we're seeing. But hopefully, after we go through this, you'll understand some of the reasons for that higher GOR, and that it's not something to be concerned about, but rather just something to plan for. Okay, I want to call your attention to this plot, which is a simulation of two cases. On the y-axis, I've got gas oil ratio, standard cubic feet. This is actually MCF per barrel on the y-axis, and the bottom hole flowing pressure on the x-axis. And this simulation is for a gas condensate reservoir where the dew point is 4,900 psi, and we have some mobile condensate in the real perm curves in this case. And what I want to call your attention to is that the GOR is constant with bottom hole flowing pressure until you get down to the dew point. And then as condensate begins to drop out, you're going to leave some condensate in the reservoir, so the GOR goes up, or the condensate, your oil gas ratio or the condensate yield goes down. I'm showing it here as GOR. So even in transient flow, when you get below the dew point, your yield is going to fall, and your GOR will go up. But if you're in boundary dominated flow, the yield will fall even further, or the GOR will rise even further. And that separation between a transient GOR and a boundary dominated GOR is telling you something about the size of the reservoir. And I'd call your attention to the Bowie and Ewert paper. As Matthias mentioned, Braden Bowie's paper refers to this difference between transient and boundary dominated flow behavior. And it's very useful and diagnostic when you're trying to tease out what is the drainage volume that your infill well is seeing. I also want to mention that in transient linear flow, as I mentioned before, gas oil ratio is controlled solely by your bottom hole flowing pressure. But once you get into boundary dominated flow, it's controlled by bottom hole flowing pressure and average reservoir pressure. So in this simulation here, I know that boundary dominated flow started here about 125 days. And again, I'm plotting bottom hole pressure on the left y-axis, the black line, and the red line is gas oil ratio on the right-hand axis. And what you see is that the GOR begins to rise really about the time you get into boundary dominated flow. And it continues to rise as we reduce bottom hole pressure. But then if you make a perturbation in bottom hole pressure and you suddenly reduce bottom hole pressure, say in this case from 3,000 to 1,000 psi, you get a huge spike in gas oil ratio. And then if you bring your bottom hole pressure back to the trend that it was on, the GOR will gradually come down and return to the trend it was on. So even in boundary dominated flow, bottom hole flowing pressure has a big effect on your GOR. So I just wanted to make it clear that it's not one or the other, but it's actually both when you're in boundary dominated flow. One of the effects you may see when GOR begins to rise is that your oil productivity in an oil reservoir may drop because of the increase in gas saturation, which causes a decrease in relative permeability to oil. This is happens to be a Merrimack example, and it's a relatively severe example of as your bottom hole flowing pressure is falling and goes below bubble point, which in this case is about 4,500 psi, GOR begins to rise and the oil rate begins to decline much more steeply than the decline you were on before. And that's simply because it's a volatile oil reservoir, and when your bottom hole flowing pressure goes below the bubble point, you suddenly have a significant gas saturation. And some of these volatile fluids, you may go from 0 gas saturation to 40% over 200 or 300 psi of pressure drop, which causes a sudden decrease in the relative permeability to oil. And that's why you see this increased slope or decline rate. Almost imperceptible, the change in decline rate. But I just wanted to point that out because it can happen and you need to understand the reasons why. Okay, so now we'll talk about how the GOR increase during boundary dominated flow is related to drainage volume. So to illustrate that, I've made a simulation of 3 different cases. And here I'm showing average reservoir pressure on the left y-axis, which are the lines, the colored lines that start up here at about 3,700 psi. And you can see for the largest oil in place, the average reservoir pressure falls the slowest. So I'm plotting on the x-axis cumulative oil production per foot of lateral. GPI is an abbreviation for gross perforated interval. So what I'm doing here is dividing cumulative oil production by the length of the lateral, so I can compare different length laterals. But in this simulation, I've got 3 different oil in places. Everything is the same, basically, except the size of the reservoir. And these are fully penetrating fractures that go to the edge of the drainage volume and the entire height in every case. So what you see is that with the largest oil in place, the average reservoir pressure falls the slowest, and the GOR, which are the upward curving lines, and on the right-hand axis here, your transient GOR in this case is about 3,500 cubic feet per barrel. And you can see the largest oil in place has the slowest rise in gas oil ratio if you plot it as a function of cumulative oil production. And this is an important concept when you're looking at GOR that you need to plot it versus cumulative oil production, not just versus time. And then as I reduce the oil in place, the second case has half the oil in place of the previous one, and the third case has half the oil in place of that previous one. What you see is that the reservoir pressure reaches a low level at about, if you want to say 1,000 psi, at about half the cumulative production of the previous case. So we're starting out at about 85 here and about 42 barrels per foot for the medium case, and for the small case, about 21 barrels per foot. So cutting it in half each time. So as the reservoir pressure falls with cumulative production, your GOR is going to rise because the basic PVT tells you as your pressure on the oil phase goes down, gas comes out of solution and creates more gas saturation, which increases the relative perm to gas and decreases the relative perm to oil. So you see an increase in GOR. And what I'm saying is that that increase in GOR is proportional to the drainage volume that the well is seeing. So here's an example, a field example of 5 wells that were drilled in a pattern here. So you have 2 edge wells and 3 interior wells, and then there's an unbounded well off here by itself in the same reservoir with the same PVT, so you can see how all of these behave. If you look at just the unbounded well and you plot, as on the previous plot, gas oil ratio versus cum oil per foot of lateral, what you see is a very gradual rise in the GOR of that parent well. And this is something like 3 years of history. Then if you look at the half-bounded wells, which are the wells on the edge of this developed pattern, you see that they start out in a similar GOR, but they rise a little bit faster. And you can see out here towards the end, they're beginning to curve up quite a bit more than the unbounded well is. But then if you look at the fully bounded infill wells, you see they have a pronounced upward curvature. And they're going, I mean, it looks like they're going to go vertical pretty soon at around something, in the range of 25 to 30 barrels per foot. So this is characteristic behavior you see for wells that are going from unbounded to tightly bounded. And that's one of the ways you can get an idea of whether your wells are bounded and seeing each other and how restricted their drainage volume is. So you can actually make an estimate of oil in place using this behavior, just looking at GOR versus cum oil per foot. Now, I'm assuming that all of the bottom hole flowing pressure schedules are very similar and that that's not having a big effect on the character of these curves. So it will have an effect. So if you have vastly different bottom hole flowing pressure schedules, you have to take that into account. But let's look at one of those bounded infill wells that's curving upward quickly. And what I did was a simple history match on this well using accurate PVT, which Whitson can certainly help you with, by the way, especially in these volatile reservoirs. If you history match one well, the oil in place that I came up with for that history match was 123 barrels of oil per foot of lateral. So you can multiply that times whatever your length of your lateral is to get the drainage volume that that well is seeing. And then I changed the oil in place in that model, just like on the previous simulations I showed you, to see what that GOR trend would look like as a function of cum oil with different GORs. And what you see is typically if you double the GOR, double the oil in place, your GOR is going to reach that steep slope at about twice the cumulative oil production. So once you've made those simulations, just varying the oil in place, you can then lay your other wells on that same plot and get some idea how much oil in place each of those are seeing. And what we see from here is that the infill wells look like they're seeing something like 100 to 123 barrels of oil per foot of lateral. And the half-bounded wells are seeing something in the neighborhood of, between 150 and 200. And then the unbounded well is seeing more than 250 barrels per foot. So by doing this kind of thing, if you have similar PVT, similar bottom hole flowing pressure schedules, you can actually read a ballpark estimate of the contacted oil in place. And what this is showing you, especially in early time, is the amount of oil that you're efficiently contacting. If you have some very long fracs that are contributing a small amount initially, but a growing amount over time, you're going to see like this parent well not following that behavior because it's not a bounded well. Essentially, you have feed in from reservoir that's not stimulated. You have some very long fracs whose contribution increases over time and will not necessarily follow this behavior. And this is a little more clear on this plot. When you're dealing with field data, as you can see here, it's very noisy. This is a daily gas-oil ratio here. But you can use a cumulative gas-oil ratio instead, which is simply cumulative gas production divided by cumulative oil production. And that gives you a very smooth curve. But you see the exact same behavior. And all I've done is convert these simulated curves to cumulative oil production per foot of lateral versus cumulative gas-oil ratio instead of instantaneous daily. So you get a very smooth curve, but what you see is that the half-bounded and the unbounded wells are not following these curves. Their effective drainage volume that they're seeing appears to be growing over time. So they cross across these curves as the edges of their drainage volume becomes more dominant of the well's production. Okay, so far we've just talked about gas-oil ratio and cumulative oil production, but now we're going to talk about how pressure normalized rate is related to drainage volume. I'm going to show you a series of curves that look like this. This again is a simulated case, and what I'm plotting here is pressure normalized oil rate on the y-axis. So this is oil rate divided by initial reservoir pressure minus bottom hole flowing pressure. So it's similar to a productivity index, except that we're using initial reservoir pressure instead of average reservoir pressure, which is what classically is defined as the productivity index. And of course, this is the same normalized rate that we use in RTA, in normal rate transient plots. So this is the pressure normalized oil rate, the green line with the scale on the left. And then I'm showing the gas oil ratio on the scale on the right with the red line here, both plotted versus cumulative oil production. So for this particular simulation, I've simulated only one stage, so an element of symmetry, for a 660-foot spaced bounded well, so a fairly tight spacing. And you do see this typical upward curvature of the GOR with cum oil that I pointed out before. You'll also notice that the pressure normalized oil rate at about 15,000 barrels from this one stage begins to decline more steeply. And that's because that's where the bubble point is that's where the pressure near the well is reaching bubble point. So you have gas saturation forming, which causes the steeper decline that I pointed out on the earlier field case. One really helpful thing about this plot, if you plot log of rate or pressure normalized rate versus cum oil, a straight line on this plot is an exponential, a hyperbolic exponent of 1. So a B factor of 1 gives you a straight line on this plot. And you can very quickly see, is my B factor greater than 1 or less than 1? A B factor greater than 1 is going to give an upward curvature, and a B factor less than 1 is going to give you a downward curvature like you're seeing on this plot. And you can clearly see that it may have been about 1 early on before you get to the bubble point, but then it's getting steeper, and as it curves downward, that's telling you your B factor is getting lower. And I would also mention that rather than just using instantaneous GOR, you can use cumulative GOR on this plot, and the interpretation is the same. Okay, so with that introduction, I want to say that what I've done here with simulation is use some pretty unfavorable rel perm curves where gas begins to flow very easily once you go below the bubble point. So you see that kink in the productivity curve. Now you will encounter reservoirs where you do not see that, and that's what I've attempted to show here with rel perm curves number 2, without getting into what those curves actually are. If you use rel perm curves that are more favorable, where gas doesn't flow as easily once it comes out of solution, then you'll see a much more gradual rise in the GOR. And as a consequence, you'll also see much less of a steepening in the oil rate decline. or the pressure normalized oil rate decline. So you can see this much difference in the exact same reservoir, same oil in place, just due to different rail perms. Now, normally in the same reservoir, you're going to have the same rail perm. So this isn't a problem when you're comparing one well to another in the same reservoir, but it's something to be aware of, that some of the GOR increases I'm showing may look surprising and very steep, but that's just because of the rail perm assumptions that I've made in the model. So here again are two simulations at two different spacings. So the pair of curves that is farthest to the right on this plot was at a well spacing of 660. And then I have reduced the spacing to a well spacing of 330 feet between wells. So half the well spacing in this left pair of curves. And you can see that they are basically a scaled down version of the larger oil in place curves. You're essentially scaling those curves with the cum oil on the x-axis. One thing I want to point out about these curves is that the productivity on the 330 spaced well is less, which tells you that by putting your wells 330 feet apart, you're cutting off some of the frac length that would have been available to the well had they been spaced farther apart. So the pressure normalized oil rate starts off at a lower rate at the tighter spacing than it does at the larger spacing. So both the productivity and the oil in place are reduced in this 330 case. So the point is that the shape of these curves, the GOR curving up and the pressure normalized rate curving down, will roughly scale with oil in place. So you can see from looking at these plots that the wider spaced well is seeing roughly twice the oil in place of the 330 spaced well. Now again, I'm assuming the same reservoir, same PVT, and same bottom hole flowing pressure schedule. I also wanted to point out that if you do have different productivity, and in this case I've got two simulations that are both spaced at 660, but the schematic over here on the left shows that one of those doesn't have the fracs completely going to the edge of the drainage volume for the 660 spaced well. So in these diagrams, you can see the well bore coming into the one stage I'm simulating. And then I have limited the well bore to halfway between wells. If you have two wells that are spaced 660 apart, then you can drain about 330 on each side of each well. So you have a total drainage width of 660. But in this middle case, you can see that the fracs don't go all the way to the edge of the drainage volume, whereas in the lower case, they do. So you have more productivity in the lower case, which is the set of curves that's farthest right on this plot. So even though these two sets of curves on the far right have the same oil in place, they have different curves for pressure normalized rate and for GOR simply because of the productivity. So you can see that the fully penetrating fracs case has a higher productivity to begin with, and then curves down at a higher cum oil out here at the end, simply because you're accessing that oil in place more efficiently than you are with the case that doesn't have the fracs completely penetrating. So you can't just look at these plots, which I'm calling quick look plots, and say that they always scale with oil in place. You have to take into account whether there's a difference in productivity as well. But the reason I call them quick look is because you can quickly look at them and get an idea how much oil or gas in place a well is accessing. It's a great way to rank wells in terms of what their EURs are going to be, although the shape of the curves can change over time, especially if you're comparing infills to parent wells, which I'll get into a little more later. So here's a field case where I'm showing 4 wells, same type of plot we've been looking at. I've added a little wrinkle here where I'm plotting not only pressure normalized rate, which is oil rate divided by delta P, but I'm also dividing that by the lateral length, the gross perforated interval. So this is pressure normalized rate divided by lateral length on the y-axis, and then on the x-axis is cum oil per foot of lateral length. So I can compare wells that are different lateral lengths. And what you see here is the black line is the parent well. And you can see it's nearly a straight line, which tells me this well has a B factor of 1 or so, maybe a little above 1. And the black line on the GOR, which is curving upward, is also for the parent well. So you can see it started off here around 3,200 cubic feet per barrel, and now it's up to about 4,600 after producing 31 barrels per foot, or I guess that would be 310,000 barrels for a 10,000 foot well. And then the infills, you can see, are draining progressively less. This may be an edge well here that's shown in red. And then you get over here to the most bounded or the poorest infill. And what you see is that it's draining, something on the order of half of what the parent's seeing. And both the pressure normalized rate are responding to that smaller drainage volume, and the GOR is going up quicker as well. So you can quickly look at these and see, well, obviously the parent's is the best well, and you can rank them in terms of how they all compare to each other. You'll also notice that a couple of these wells start with productivity that's nearly the same as the parent, but the worst well does not. It has considerably lower productivity when you're starting out early on. So let's look at that same plot in a gas condensate reservoir. And so what I'm plotting here is the normalized gas rate, which in this case, you can do this a couple of different ways. Normally, when we talk about normalized gas rate, it's gas rate divided by the difference in pseudo-pressure for initial reservoir pressure minus pseudo-pressure for the wellbore pressure. But in this case, I'm doing it just as a straight pressure difference, PI minus PWF, just like the oil case. And you get essentially the same curves doing that. Now, in this case, since it's a gas reservoir, starting out 100% gas in the reservoir and then dropping out condensate as the pressure goes down, I'm plotting the gas condensate ratio, which is on the right-hand axis over here. And you can see we're starting out at a GOR of 6,200 cubic feet per barrel, which is obviously a gas in situ. And then you have a gradual rise in the GOR for the red curves as you're depleting that reservoir. So again, a straight line on this plot is a B factor of 1. You can see that it's concave upward, both of them are. So you've got, in terms of the gas phase decline, a B factor greater than 1 in this case. But obviously the red well is producing, is accessing a reservoir that's something over twice what the blue well is accessing. And it's easy to see by the way these curves relate to each other. Okay, let's take a look at the difference between parent and infill GOR behavior, because that's what a lot of us are dealing with these days. Again, a simulation here. It's a simple generic model using generic PVT. And it's just a single layer model, and I have an unbounded case, which you see on the right here with some very non-uniform frac length, and a bounded case, which you see on the left, which in this case is about a 660 well spacing compared with an unbounded well that might have 1,000, 1,200 feet long half-length fractures, at least a few of them. And if I run that simulation for 5 years using the same bottom hole pressure schedule, I'm going to show you a couple of plots here that we'll look at a little bit more. But this is oil rate versus time, in this case, date, and the production is starting in year 2000. The U is the unbounded case, the B is the bounded case. So I'm just referring to these two cases, the unbounded and bounded cases, again, simulating about a stage. And you can see the unbounded case has a much higher oil rate because the fractures are completely unobstructed and the well has access to the entire length of the fractures. But the bounded well's fractures are cut off by the boundaries of the reservoir. So if you look at the oil rate on the left axis and the GOR on the right axis, you can see that the unbounded well has a very gradual rise in gas-oil ratio, while the bounded well has a quicker rise in gas-oil ratio versus time. And we'll look at the plots versus cum in a few minutes. Then if I plot the same data, I'm showing that both cases use the same bottom hole pressure schedule, starting out here at time zero around 9,500 psi. This is a high pressure reservoir, and declining smoothly over time to 1,500 or so after 5 years. And then looking at the cumulative oil production, you can see the unbounded case produces maybe 2.5 times what the bounded case produces, as you would expect. So no surprise about that, but do notice that the bounded well GOR goes up quite a bit quicker, simply because there's less oil available to it. And now I want to show you a video, a time lapse of the simulation, just so you can get an idea how these wells are draining differently. So what this is a pressure profile, and the scale, I'm going to stop this so you can see it. The scale goes from initial pressure being red, so red is virgin pressure, blue is the low pressure, which of course is lowest at the wellbore. And you can see as time goes on, the unbounded well, in this case, after about 9 months or 8 months of production, the unbounded well still has virgin reservoir that's being drained by these long, you might call them runaway fracs. While the 660 spacing well has no virgin pressure available to it, and its entire drainage area has been depleted, at least to some extent. So if we run that on out, what you see is that after a year, we're now at a year, the pressure is getting lower and lower in the infill well reservoir, whereas the unbounded well still has virgin pressure out here on the edges. And as a result, your gas-oil ratio is going to be lower in the parent for a much longer time, because you have undersaturated oil out here on the edges still contributing to production. Whereas the infill well has almost completely depleted its drainage volume in about 5 years. So if you look at that in terms of gas saturation, which is really what controls your GOR, just the same time period here, but we're showing gas saturation, and we run about 5 months, and at that point, the bottom hole flowing pressure gets below bubble point, so you see gas saturation starting to develop. But again, you have very little volume that has no gas in it in the bounded well case, but a lot of volume that has still 100% oil saturation in the parent well case. So this is just to help visualize why a parent well GOR is much, much flatter than a bounded well GOR if the bounded well is drilled on tight spacing. Obviously, the larger spacing you drill on, the closer you get to parent well performance. This is just summarizing what I've already said. Now, if you look at those plots that I showed you earlier, they are the two plots on the top, the exact same production histories here. But then if we plot them versus cumulative production, which is much more informative, what you see is that the bounded well has a quicker GOR rise than the unbounded well. And then the lower right plot is the quick look plot that I mentioned to you. And what you see is that the parent stays at a constant GOR for a much longer time and rises much more gradually than the bounded well. So in this case, the bounded well is at 660. So I could run cases at 990, 1320, and those GOR curves would fall in between the bounded and unbounded cases. And the productivity curves would also fall in between those cases. So this is a way to get an idea what larger spacings would do and to understand why. Hopefully this gives you a feel for why parent GORs are sometimes much flatter for a much longer time than bounded wells are. Okay, so we have covered the fundamentals of GOR and linear flow, how the GOR increases during boundary dominated flow, and how that's related to drainage volume. We've talked about how pressure normalized rate is related to drainage volume, and how you can use it to diagnose the size of reservoir your well is accessing. And we've discussed the differences between parent and infill GOR behavior. And we've also talked about the need to be very humble when you're doing spacing tests, because you always learn a lot as you drill on different spacings about what you should do the next time. I'd like to thank Cimarex management for allowing me to present this information, and would like to thank all of you for listening.
Awesome. Thank you so much, Steve. Second time I've seen, I think there's some updates since last time, but always learn something new, which is great. We've got a ton of questions, and that's why I didn't have, I guess, the conscience to interrupt you in the middle of the presentation with some questions. But I'll start with some low ballers, because a lot of you have asked about the recordings, if they will be made available, and the answer to that is yes. We'll get that out as soon as possible. The second question that come a lot is more a logistical thing for you, Steve. Is will the slides, can they be made available, or do you have?
Yes.
Yeah.
Yeah,
okay.
I can make those available.
Awesome. And I've gotten such a long list of questions that I'm afraid I can't. We'll probably not be able to go through all of the questions, but
just pick the easiest one, Matthias.
That was exactly what I wanted to do, to pick the easiest ones, the ones that I almost could answer. The first, which is a little bit more practical, for people to get a little bit more context of the work you've done. What tool did you use to perform these simulations? Has been asked by a few different folks.
Okay, well, I was using Sensor in this case, and with a front end and back end that's made by a company called Santec. But you can do the same thing in the Harmony numerical simulator or any number of other simulators.
Yeah, and you've so what you're saying is that the results you've seen in other simulators as well, and it's not necessarily a sensor-specific observation.
As long as you get your grid fine enough, awesome, so that you don't have any numerical dispersion problems.
And I guess so a little bit along those lines in terms of some of the physical parameters that you've used for the simulations. A lot of people are asked about questions related to permeability levels that you've used in the model, and also call it effective frac-to-frac spacing or cluster spacing. Can you make a couple of comments?
I think for these, something like 35-foot cluster spacing, on the order of 200 nanodarcies for the perm. And this was a initial reservoir pressure of 10,000 psi, and the bubble point, I don't remember, it was around 4,500, I think. So a volatile oil, light volatile oil, and high pressure, pretty good perm.
Very good. Very good. And I think you actually answered one question that I thought was a little bit interesting related to fluids. Was some of these observations and your original GOR paper from 2016 was mainly focused on oil systems, but you touched a little bit upon it here, where you've seen and you can kind of apply a lot of the same, I guess, methodologies and diagnostics to condensate systems and air critical systems as well.
Yes, yeah, I've found in practice that it does, you can use the same concepts for condensate systems. That may not apply to all reservoirs, but for the work I've done in the Permian and the Anadarko Basin, it seems to work quite well.
Very good. And I see there are still like a million questions that's coming in here, but when it comes to the topic for today was kind of parent child and infill drilling related. Do you have any comments, observations on GOR behavior when wells are hit by offset fracs, which I guess is a little bit along the same lines?
Yeah, usually there's a decrease in the GOR because the pressure goes up as a result of the frac fluid increasing the pressure around the well. So you'll typically see a temporary reduction in GOR. And of course, if you get a lot of water in the parent, the producing pressure, bottom hole flowing pressure of the parent also goes up, which also reduces your GOR. So typically a temporary reduction in the GOR that will recover to its initial level over time, or its pre-frac level.
Very good. So the first question we got, which was interesting, was a little bit related to some of the theory you covered, and how kind of bottom hole pressure is linked to I guess GOR performance. And just to clarify that, because you're talking about bottom hole pressure, at least during infinite acting flow, being a main driver on GOR. So the impact of changing bottom hole pressures, either increasing or decreasing, has an instantaneous impact on GOR. Is this correct to assume in all cases? Do you have any comments to that, Steve?
Well, we do. There are cases where well, in general, if you have high conductivity fractures and a good connection to the reservoir, yes, the GORs, as soon as you go below the bubble point with your bottom hole flowing pressure, I didn't talk about this, but critical gas saturation. If your rock has a critical gas saturation, the gas won't begin to flow until it reaches a level, say 5%, 10%. To where it will form a continuous phase and begin to flow. So in that case, theoretically, you should see a reduction in your GOR while that gas saturation is building up, and then you'll see a rise in your GOR as it begins to flow. So that's one thing that can delay the rise in GOR. There are reservoirs, the Wolf Camp in some places, where your bottom hole flowing pressure goes below what you know is the bubble point from PVT studies, and yet you see no rise in GOR until you go well below the bubble point. And I can't say that I or anybody I've talked to completely understands that. It may be due to the wellbore pressure not being efficiently translated to the formation face that you're producing from, like low conductivity fractures or some sort of pressure drop or skin between the wellbore and where your production is coming from. Can also be due to critical gas saturation. And another possible cause is what we call nanopore bubble point suppression, where the pores are so small that you don't get normal bulk PVT behavior in those small pores, but you actually have a smaller or lower bubble point. So those are all possible explanations for when the GOR doesn't rise when your bottom hole pressure goes below the bubble point.
Yeah, very good. And actually, that last comment you made with regard to kind of bubble point suppression, I think there's not a single PVT session in unconventionals that there's not a question or a throw-out comment, what about bubble point suppression? So there was a few questions related to that as well. Have you looked at the impact of bubble point suppression or kind of this pore size distribution and how that affects GOR behavior? or is that something you'll plan on looking at, or do you have any sense of related to
Well,
that?
it's always a possibility. It seems like, at least in my experience, it's been possible to explain the behavior with other things like a pressure drop between the wellbore and the and the formation face. Um, and it hasn't been necessary, at least for me, to say that that's a controlling factor, but I know the physics says that it is at certain pore sizes. So I haven't gotten deeply into that. I mean, I've read papers like everyone else where you use basic physics models to predict that, and it is a real phenomenon. But I guess personally, I tend to look for other explanations before going to that.
Very good. And I can say, at least from our shop, we've seen, we kind of share that experience, I think, as well, Steve, that there's enough knobs in the conventional toolbox to turn to match producing GR behavior. Leaving fluids a little bit on the side here. Have you seen any in terms of call it rock properties, and how potentially rock properties are changing spatially, either vertically or aerially, how that can impact GOR behavior over time? I think you touched a little bit on, or at least commented, layering in maybe some of the one-on-one sessions we've had, Steve, and how that can impact these results. Can you share a few
Yeah,
sentences?
it has a huge impact. I mean, if you're producing primarily from a very thin high perm zone, early on, most of your production may come from that. But as that depletes, maybe most of your storage is in low perm rock, and that will deplete much more slowly. So what you're seeing at the well is actually a composite of the production of all those different layers. And so yes, I've only shown simple single layer models here, but I've run plenty of multi-layer models, and it has a big effect on your GOR. I can't say that how exactly it changes your GOR behavior, because it just depends on what the reservoir system is. But you always have to keep in mind that what you're seeing at the well, at the surface, is an average of everything that's going on downhole. And in fact, I think Whitson Curtis presented a paper recently about that, about the GOR behavior at the surface being controlled by a lot of different things, stratigraphy, porosity, and perm. And so you're seeing an average at the surface.
Very good. And along those lines, when it comes to for instance, we talked a lot about fluid and kind of fluid rock. And what about the fractures? Have you looked at sensitivities to kind of degradation of fractures versus time, and how that impacts the GOR behavior? Or is that something on the to-do list, or consider it important?
Well, no, I consider it important. It's it's difficult to characterize, but yeah, we have seen data that indicates you are definitely having a change in conductivity over time in some places. So yeah, it can be very important, and so it's partly related to how you draw the wells down, and we think it's. I guess I'm becoming more convinced it's important to have a smooth drawdown profile, and not a lot of sudden changes in your bottom hole flowing pressure, things like that, just to maintain the integrity of the fractures for as long as you can.
Very good. And if we bring this kind of work that you presented now and compare it to that paper in 2016, what are the kind of the main differences and the kind of the new findings in your work for the people that a lot of people have asked about, kind of that paper versus a few of the things you talked about here, and not to mention, will there come like a Steve Jones GOR paper 2.0 sometime soon?
Um, well, yeah, the main difference here is that I'm focused on boundary dominated flow, whereas the early paper was really talking about the transient period. And we don't see much of a transient period anymore with the way we're completing the wells. Um, so that's the main difference, is just what you can get out of that boundary dominated flow. Because as everyone knows from their petroleum engineering training, you really can't diagnose the size of the reservoir except for a minimum until you get into boundary dominated flow, because the production isn't responding to the boundaries of the reservoir. So the main difference is trying to diagnose information about drainage volume from boundary dominated flow. And as far as whether I'll publish this, it hasn't been published by me yet. Some of the stuff you'll see from Braden Bowie and others does get into that. So yeah, I just haven't had the time or ability to get that published yet. So no plans in the works right now.
Very good. So it seems that there will be a very natural continuation, I guess, of this presentation in the next webinar with Braden in a couple of months. I guess first of April. On that last note, there's also, I mean, I don't think we've ever gotten that many questions before, actually, and it's still coming in, several ones on the chat privately and in a Q&A session. So the last question that I'll ask Steve is related to kind of diagnostic plots. Is kind of the diagnostic plots, some of the plots you've used and showed in the presentation, have they been standardized, and is that something that Cimarex is using on a day-to-day basis, or is that the plan going forward, or is there any work left that has to be done before you get to that point?
No, we've been using these plots for quite a while. Yeah, they're fairly well standardized. I mean, they're simple to make, and there's nothing mysterious about them. You do have to have daily pressures, so either estimated or measured with gauges, and we're having more and more wells that have measured bottom hole flowing pressures, which makes these plots much more accurate and very easy to do. So yeah, they're pretty standard.
Very, very good. So, and I see there's a million questions here, and I'm sorry that we can't answer all of them. What I'll do, though, is that I'll save all of the questions in a summarized email to Steve, and if you have any questions, I guess they can contact you for questions, Steve, or how?
Yeah, they can. Yeah, I've got my LinkedIn address there at the end of the slides, and that's a good way to do it so that my company email doesn't get flooded. But sure, I'd be glad to take questions later.
Very, very good. And thanks so much for everybody that joined the webinar today. And thanks to you, Steve, for sharing this presentation. And at least I will look forward to hopefully a potential future paper where a lot of this is summarized. And to all the participants, thank you for joining. And if you have any questions related to anything, the logistics of these webinars, the courses we talked about as an introductory note, just let us know. You find all our contact information on Whitson.com. And until next time, stay safe and healthy. There's fairly strange times around in the world, so be careful until we hopefully meet again. Thanks again. So bye-bye, everybody.
Thank you.
Thanks again, Steve.
Thank you, Curtis.